we're going to look at the integral over the curve C of y sine z ds. And C here is the circular helix given by the parametric curve cosine t for x, sine t for y, and z is going to be equal to t. And we're going to do this over the interval from 0 to 2 pi. So first, let's grab our general form for finding a line integral. Just so we can remind ourselves, we take the integral over the closed curve C of f of r of t times the magnitude of r prime of t dt. So this is really the integral over C of f of x, y, z ds. But for these line integrals, the ds is this magnitude of r prime of t dt, and f of x, y, and z gets replaced with f of r of t, where r is the parametrically defined curve C. So here we've got our parametric setup. It's not listed as r, but that's okay. We're going to make it an r of t really quickly. So this is going to be cosine t, sine t for y, and t for z. So now we can go ahead and take its derivative. So we can start working on that ds. So we'll find r prime, which is minus sine t, cosine t, and 1. And we need the magnitude then of that. So magnitude of r prime of t is going to be equal to the square root of sine squared t plus cosine squared t plus 1 squared, which is 1. Of course, we know that sine squared plus cosine squared is equal to 1, so this just turns into the square root of 2. So now I've got what I need to replace in for our magnitude of r prime of t. Now we take the parametric definition for our curve and sub it in to the f of x, y, z. In this case, that means taking y to be sine t, and z we're going to replace with t. And again, ds is going to be our root 2 dt. So now I've got the integral from 0 to 2 pi, because that was our range. Again, making our replacement, we've got sine t times sine t times root 2 dt. Okay, just simplifying that out, I get the square root of 2 times the integral from 0 to 2 pi sine squared t dt. And I think you guys can finish it out from there.